In this video, we will be looking at some optimization exercises, mostly taught in Calculus 1. So the overall process here is you want to first just make a note. It can be a mental note, or I'm going to write them on the slides, of what you are trying to optimize. The second part would be to write down what you're given, draw a picture, and create some sort of equation given from the given information that you know. And some of it you'll have to create on your own. You'll see when we get there. The third step is we want to write the optimization equation, and then make sure we can write the optimization equation in one variable using the equation we found in step 2. The last of it is that we need to find the derivative of the optimization equation, and then we can find the critical values and find maxes and mins and do all this fun stuff. So without further ado, in this particular exercise, we're looking at a box with a square base and no top. That is important. No top. And this box has a volume of 108 cubic feet. So we're trying to find the dimensions of the box with the least surface area. So the first thing you want to do is, what are we trying to optimize? Well, we're trying to optimize the surface area, and I will abbreviate SA for surface area. The next thing, what do we know? We know the volume is 108 cubic feet, and we have a box, so I'm going to draw a picture of that. Your pictures could be given. You might have to draw your own. And I'm going to draw this extra line here to show you that this box is open on the top. So we know this box has a square base, so I'm going to give it some dimensions x. We don't know how long the side of the base is. And we don't know how tall, so I'm going to call the height h. And with this particular box, I also know, this is the first of the equations we are trying to figure out, that the volume equals x squared h. And I can remember back here I have this volume and this volume. So if we know the volume is 108 cubic feet and the volume of the same thing is x squared h, then I can write this new equation right here, that x squared h equals 108. And I'm going to forget about the cubic feet for now, but at the end we will bring these units back. The third step we're trying to do here is we're trying to find this optimization equation. So the surface area here would be the 4 walls, right? There's one here, one in the back, and one on the right side. So we have 4 walls, and they will each have an area of xh. And I can tell that because right here, the base of this particular left side, this face, the base of it is x, the height of it is h. Base times height is how we can find the area of this one. And there are 3 others exactly like it, so there are 4. But then we have a bottom that we can't quite see here. So it looks like this maybe here. And we only have one bottom, and that area will have an x squared. And if we wanted to take the derivative of this surface area as is, we would have a problem, because we have this h, and that's going to muck things up. So what we want to do down here in a light green color is solve this equation for h. And the reason you want to solve this equation for h is because if you solve for x, right, which we would need an x, right, we have x squared and x here. If we solve for x, then we have to start considering, well, is the square root going to be positive or negative? Because when you take the square root of an x squared, you get a plus and minus square root of whatever it is on the other side. So we definitely want to solve for h here, and this would mean h equals 108 over x squared, and I want to put this in here for h. So now we would have this in a one variable over here on the right column. SA would be 4x times 108 over x squared plus x squared, and this is the equation we are trying to optimize. Now I wouldn't quite do it yet. I would simplify it like this. Then we can take the derivative. So if you push this up to the numerator, it would be x to the negative 1 power. And so the derivative of the surface area would be negative 432 over, and if I push it back into the denominator, over x squared plus 2x. And our goal now is to set this equal to 0 to solve for x. And before I even get to that, I want to make absolutely sure that everybody out there understands the following. Since there is a variable in the denominator of our derivative, I have done no solving yet, and since this variable is in the bottom, this has a chance anyway, to create another critical number. So here we go, x squared in the denominator. If you set that equal to 0 and solve for x, you get x equals 0. So there's a critical number for this particular derivative. But I also very quickly want to dismiss this critical number. Think about it back over here in terms of the picture. If you have a base, a square base, and the side of that square is length 0, that's not going to make any sense. That will make 0 sense, especially when you try to solve for the height here. When you substitute 0 over here, you can't divide 108 by 0. That doesn't make any sense. So just as soon as we found this critical number, it is also gone. And that's just because in the real world it doesn't make any sense to have a box with any dimension length 0. Alright, so now that we've gotten that out of the way, I want to go through and actually solve this. So you can solve this by multiplying each term by x squared. That's how you're going to get rid of the derivative, or get rid of the denominator here. And what you will be left with is negative 432 plus 2x cubed equals 0. And if you add 432 and you divide by 2 and you solve for x, taking the cube root, you get 6. So what that means now is 6 feet. What that means now is that each dimension here for the base is 6 feet. So we have a bottom of this box that is 6 feet by 6 feet. And if we take this value and substitute it back in here for x, we can easily find the height. The height would be 3 feet. So all of this over here would be step 4, right? We got it in one variable. We simplified this equation down so that we could take the derivative. This is the one step of calculus here. And then we went through and figured out, actually solved for x. And since this critical number didn't work, we didn't have to worry about that. Let's take a look at the next example. You are designing an athletic field in the shape of a rectangle with a semicircle on each end with radius r. The boundary of the field is a 400-meter track. What values of x and r will give the rectangle the greatest area? So this looks something like this. If we have a semicircle on this end, we have a nice rectangle in the middle and another semicircle over here. Here is radius r, and here is what is being mentioned as x, the straightaways, if you will. So we're trying to maximize, give the greatest area to the rectangle. So we're trying to maximize area of the rectangle, and I'll abbreviate rectangle. So this area right here, something like that. So that was the first step. The next step, we want to write down what we know. Well, we know that the perimeter of this loop is 400 meters. That's a long distance, all right. And the perimeter here, just based on the picture, is the circumference of a circle. And I'm going to use 2 pi r here instead of pi d, because we are basing things with the radius, plus 2x. So the 2 pi r takes care of the entire circle on the ends here. There's a semicircle and a semicircle making a whole circle, and 2x straightaways. So if you combine these two together, you'll get 400 equals 2 pi r plus 2x. And the area that we are trying to maximize for step 3, right, our optimization equation, is this rectangle here. Now you can see that this rectangle has a length of x and a width of, this is actually going to be 1 diameter of this semicircle. And again, in terms of the radius, that is 2 radii. So the area will be 2r times x. So then we can just either solve this equation for x or for r. It doesn't matter which one in this case, because we will not be worrying about any square roots here. But I am going to choose to solve for x, and that way we can substitute this right into this equation, our optimizing equation. So if we solve this for x, we get x equals 400 minus 2 pi r all over 2. And you can either reduce this here, or you can divide 402 and 2 all by 2, or you can just take this and substitute it into the area equation to get a equals 2r times, instead of x, we will have 400 minus 2 pi r all over 2. And these 2's will reduce. So you can either reduce the 2 in the denominator here, or you can do it here, or you could have done it in the original equation. So now we can have this, the area is r times 400 minus 2 pi r. And to make this even simpler, I don't want to do a product rule here when I find the derivative. So I'm going to take this r, multiply it through, and get a equals 400r minus 2 pi r squared. Now that this is about as simple as it gets, we can use the power rule here instead of a product rule we would have to use over here. Now I can just take the derivative pretty easily and just say a prime is 400 minus 4 pi r. And so if we set this equal to 0, and I'm going to make a point to say this here, we don't have to worry about where this derivative is undefined. I don't see any r's in the denominator. In fact, there are no denominators here, so we don't have to worry about where this derivative is undefined. So all we have to do now is set it equal to 0 and solve for r. And if you do that, you'll see that r is 400 over 4 pi. So there is the radius. Now, this is a strange thing here. This can be reduced to 100 over pi if you divide the top and bottom by 4. But what's strange here is that we're trying to find the dimensions of the rectangle. Oh no, I guess it says what values of x and r. Okay, so if we were asked to find the dimensions of the rectangle, we would have to multiply this by 2 to get the full height of this rectangle. I think I called it width earlier. So if we were looking for the dimensions, we would have to multiply this radius by 2 to get the entire diameter. But other than that, we can just throw this 100 over pi in here for r to figure out what x is. So x will equal 400 minus 2 pi r. Oh, it's not r. It's 100 over pi all over 2. So luckily here, the pi's will reduce. 2 times 200, or 2 times 100 is 200. 400 minus 200 is 200. 200 over 2 is 100. And these are all in meters. Now, one thing you can do is approximate this distance. I would go out to maybe 3 decimal places. If you divide 100 by pi, let me see here, 100 divided by pi equals about 31.831 meters. And this is something that you would use in the real world. If you walked up to somebody and said, hey, the radius has to be 100 over pi meters, they're going to look at you funny. So if you are doing this in the real world, if you happen to be ever faced with optimizing something in the real world, you can give them the exact answer, but I would quickly follow it with something like this so that it makes more sense. People can understand 31 meters. People have a harder time understanding 100 over pi meters. So here are your answers. Let's move on to the next one. A farmer wants to create a rectangular pig pen divided into 3 smaller rectangles with sides parallel to one of the sides of the larger rectangle. He has exactly 300 feet of wire fencing to create the pen. Find the dimensions of the pen with the largest possible area. So we are trying to maximize area. We will have a rectangular pen, and in it there will be 3 equally sized pens. And it should be noted that these lines are all parallel with each other. So what we are trying to do then is we are trying to find, what do we know? We have 300 feet of fencing, and I'm going to use the word perimeter here loosely. But the entire perimeter of our shape up here, if we called this x and x and x and x, and this entire distance y would be 4 x's plus 2 y's is also the perimeter. So we can fit these two together to say 4x plus 2y equals 300. Now what is it we were trying to maximize? The area? Well, the area of this rectangle here, the big rectangle, would be x times y. So here we go, area is xy. Now again, this is in 2 variables. We don't want to optimize in 2 variables. We want to solve for one of them here. So I think I'm going to solve for y. So if you solve this for y, you'll end up with y equals 150 minus 2x. And so what's going to happen is we'll substitute this in for y. Hopefully you guys are starting to see the pattern by now. That leaves us with the area being x times 150 minus 2x. And again, we run into the same scenario. I do not want to run a product rule if I don't have to. So I'm going to distribute this x to everything inside the set of parentheses and end up with an area equation that looks like this. Minus 2x squared. All right. So now we can take the derivative. This would be 150 minus 4x. We can take this and set it equal to 0. And again, I want to point out there are no variables in a denominator, so we don't have to worry about where this derivative is undefined. all we have to do is set this derivative equal to 0 and solve for x. So again, luckily we were left with just a quadratic equation here, which made the derivative easy, which means this will be easy to solve. We will end up with x equals 75 over 2, and that's feet. I see feet up here. All right, so to figure out what y is, we can just put 75 over 2 in here for x, and we can get y equals 150 minus 2 times 75 over 2. The 2's will cancel. We will have 150 minus 75. We'll have y equals 75 feet. And I think this is going to work out just fine, because if we have 2 y's, that's 150 total feet. If we have 4 x's, the 4 would cancel with a 2 here, leaving a 2 in the top. 2 times 75 would be another 150 feet. 150 feet in x's and 150 feet in y's. Well, that leaves us with 300 total feet, just like we wanted. All right, let's get on to the last one. Find the dimensions of a rectangle of maximum area that can be inscribed in a semicircle of radius 4. Ooh. All right, so this is what this is going to look like. We will have a semicircle with some sort of rectangle drawn in here, like this. And what's key to note is that from the center of this semicircle, we can get to this point on the circle, or we can get to this point on the circle. So if you are in my actual class, I called this entire distance last class x. I goofed. The only distance I can call x is the x distance between the center and wherever that point is on the circle. So it's really this distance is x. But I was still correct when I said this distance here is y. So I only found half of the dimension for x when I did this particular example in class. Anyway, for everybody else and my students, we know that since this is the top half of a circle, and you can kind of see it here by this right triangle that's right here, we know that this would be the Pythagorean theorem of this particular right triangle would be x squared plus y squared equals 4 squared, or 16 if you will. So if we solve for y and pick the positive square root, we would get here y equals the square root of 16 minus x squared. So that's cool. That is the equation of the circle that we know, the semicircle, this part up here. There we go, this part here. What we're trying to do, if we are going to optimize the rectangle area, we need to come up with that equation. So I think the area equation here would be 2x y. And that's because here we would need 1x here plus another x. So x plus another x would be 2 total x's plus y. And luckily we can substitute this right in for the y value. So we have the area is 2x times the square root of 16 minus x squared. And this time we are unable to distribute this 2x through to make this an easier derivative. So we have to use the product rule. I'm going to pause for a few seconds, allow you to pause the video and see if you can come up with the derivative yourself. And then I will just put the derivative on screen here, see if you got what I got. So here's what I got. And in this particular case, yes, we have a denominator with x's in it. So we need to figure out what values of x make this denominator equal to 0. So we can set this denominator equal to 0, solve for x, and you'll see pretty easily that x will be -4 or 4 here. Those are what make the denominator equal to 0, right? 4 squared is 16, 16 minus 16 is 0. Your whole math world blows up if you try that. So we can't use -4 or 4, and since we're talking about distances here, or about distances here really, we're trying to find the distance of a base and a height for a rectangle, we're not going to be using -4 anyway. So we have a chance of using +4. Let's actually set this thing equal to 0 and see what answers we get here. So if we set this equal to 0, I'm going to change my notation a little bit to 16 minus x squared to the 1/2 power plus 2x over 16 minus x squared to the 1/2 power. There's a 2 here. All right, so I'm going to multiply everything by 2x, 2 times 16 minus x squared to the 1/2 power to get rid of this denominator, and it leaves me with something like this. There we go. So I can distribute this 4 through and rearrange some things to get, let's see, 64 plus 2x minus 4x squared equals 0. I can divide everything by 2 and get 32 plus x minus 2x squared equals 0. And unfortunately, I don't believe this is going to factor. So you can use the quadratic formula, and you'll see that the only positive answer you get here is x equals 2 square root of 2, or square root of 8. If you substitute that number in here for x, you'll get that y is 2 square root of 2 after you simplify it down. But this is not the entire dimension, remember. We need 2 x's over here. So really, the 2 x's will be 4 square root of 2. So these dimensions here are what are needed to make the maximum area. Thanks for watching, everybody.